Guys ready to begin? So I thought we'd start off today just kind of summing up a little bit of your simple sorts testing a little bit. Okay, I saw a lot of people turned it in, some people did not. So I just kind of wanted to talk about it a little bit. And then we'll get into our recursion. So we'll get into the recursion chapter, of course. All right? Okay. So what did you learn from doing your simple sorts, those of you who did it? Did you learn anything? Hopefully you did. What'd you learn? Kushpreet, what'd you learn?
Swaps compared to other.
What is it?
The swaps, how less it performs.
Oh, yeah, so the more swaps, it performs less. So, I mean, not performs less. It takes longer time. Jacob, what'd you learn? Did you learn anything? Nothing? You should have learned something. You should have learned that it takes a really long time on Maple, right? Did you guys actually test it? It takes 7+ hours, and then we have to stop it, right, Todd? You told me that? Yes. Todd, what'd you learn? 2 days of computing, yes. So we figured out that sometimes running a program inside of software takes a lot longer than just computing it, okay, in a spreadsheet, yes. Okay, so hopefully you didn't, well, not hopefully, maybe you did run it for the 2 days or 3 days that it did actually take to sort these things. As long as it wasn't failing, it would have completed. So Todd did stop his computer from running after, was it 2 days, right, 48 hours, of it trying to bubble sort 100,000 items. So you can see just how these simple sorts are not very efficient, obviously, okay, and why we need to have more efficient advanced sorts. If we were having all of our sorting done based on this, and we only have 100,000 items, and yes, Maple is not the most efficient programming language, obviously, but it it goes beyond Maple. It still is very inefficient. It's a very inefficient algorithm, okay? And what made that algorithm very inefficient? Hopefully you guys looked at that code and kind of interpreted it. When it stopped, when you kind of gave up on it running maybe your tests and you wanted to still complete this assignment, you had to figure out how many comparisons and swaps, these simple sorts were doing, and then you had to, calculate it, right? So hopefully you guys took it upon yourselves to kind of look at the code, look at the algorithm, and then do the calculations even if you couldn't test it. Okay, so that was kind of the thing with this assignment. Okay, you're supposed to say, okay, this is taking way too long. I'm going to figure this out. Okay, and if you read your book, they actually gave you these equations to figure out how many comparisons there were. Okay, and you could easily figure out how many swaps there were by looking at your code. Okay, and then you could fill in these numbers. Okay, you could figure out how many comparisons it is. You could figure out how many swaps it is. And then a couple of you did figure out also that Excel does have some issues. And Excel would not plot our data correctly sometimes. Yes, and we played around with it a little while. But we found a bug in Excel, and he wouldn't plot it right. But we could still get the numbers in there, hopefully. Everybody got the numbers in there. Okay? So we figured out that these simple sorts are very inefficient. We cannot do sorting in real life with these simple sorts. I mean, you can for small amounts of numbers. It worked well, right? It worked. But when your n got really large, it stopped working well. Okay? You have to move on to a different kind of sorting algorithm. Okay? And this is why we need better sorting algorithms. All right. Do you know how many sorting algorithms there are in the world? Have you ever questioned that? How many ways are there to sort things in a computer? There's over 200. Okay, I think the last one was made in 2011. So they're still being created. Okay, you can still think of a new way to sort data. Okay, so these algorithms are still being created. Sorting data is extremely important. Okay, why is sorting data extremely important? So we can find the data with binary search or with other searching algorithms. So it needs to be in order. All right. Now, all of these, sorting algorithms all did the same thing. They all did the comparisons and the swaps, and even our advanced sorts, that's what they do. They compare and they swap, because remember that a computer is very limited because it's binary. It can only see two things at once, and so that's our limitation with a binary computer. Okay? So hopefully, you guys were staring at that code trying to figure out your times. And when you're looking at this code, hopefully you notice something about it. So looking at your bubble sort, what made your bubble sort inefficient? What's inefficient about this code? What's the problem with this code? Not the problem, but the inefficiency. Todd, what made it inefficient? It made it inefficient, but it made it easy to calculate. What's the inefficient? Huh? Yes, in your for loop. I think roundabout you kind of answered that. It has a for loop in it. So it's going, so your code is iterating a set number of times. Okay? And so it made it easy to calculate because, it's a set number of times. It's a for loop, so it has to happen that many times regardless. And that many times was based on n. So when your n got really large, your for loop had to iterate that many times. But what made it inefficient also is this inner for loop. So a for loop within a for loop, whenever you see a for loop within a for loop, and your outer for loop starts at n, and your inner for loop is based on the outer for loop that starts at n, you should think n squared algorithm. Okay, so when you have a for loop within a for loop, n squared algorithm, you should think inefficient. Okay, and so the two for loops actually did make it easy to calculate because you know that this one is happening n times. And how many times is this one happening? If he's based on the other guy and looking at the equations in the book maybe even. He happens n times. How many times does that guy happen? Huh? Both of them together would be considered n squared. Yeah, n minus 1 divided by 2. Yes. So that inner for loop is happening n minus 1 divided by 2 times. Okay? And if you look at the equation, that's what you see right here. So if you have a for loop within a for loop, you can multiply this n here was for the outer for loop. And the n minus 1 divided by 2 is for the inner for loop. Okay? So you can kind of see, okay, bubble sort, really inefficient, okay, but really easy to calculate. You could have just plugged this equation right inside of your cell. In fact, I think I did that in here. You can see the equation up there. Okay, so remember that even though you maybe don't want to wait 2 days for your computer to complete this stuff, you could have still got the numbers, okay? So you should have still got the numbers here. Okay, they're actually pretty easy to calculate with inner for loops. And notice that selection sort had the same amount of comparisons. How did that happen? Well, hopefully you were looking at the code, right? When we look at bubble sort, he has that for loop within a for loop. And then he has this if statement in here, and the swap is inside of this for loop. Okay? So for loop in a for loop, if statement with a swap in the for loop. And when you look at your selection sort, what do you notice? And I had one all color-coded, but he wouldn't open here today. So, but what do we see? We see a for loop within a for loop. And what do you notice about these for loops? They look just like the bubble sort for loops. Okay, so they're the exact same for loops, so that's why they had the exact same times for comparisons. Okay, but what do you notice about the swap?
Much more efficient.
Why is that much more efficient? Because they took the swap out of the inner for loop. So notice this is the same exact algorithm as bubble sort. The only thing they did different was they took the swap out of the inner for loop. Okay? So the for loops still iterate the same amount of comparisons, but if we take the swap out of the inner for loop and it's in the outer for loop, how many swaps do we have if it's just in the outer for loop? And he made his more efficient by putting this line of code in. So the algorithm in the book actually didn't have this if statement in there. But if you had just this swap here, how many times does that swap happen? That many of times. He's in the outer for loop. So you can tell that that swap is going to happen n times. Okay? So you can kind of calculate those numbers too. Okay? You know how many swaps it is because it's happening n times. And that's what makes this algorithm a little tiny bit more efficient than bubble sort, because he takes the swap out of the inner for loop and he only swaps once per outer for loop. Okay? And then if you were looking at the insertion sort, hopefully you're looking at our insertion sort. This is actually almost the same algorithm too. Did you notice the similarities between this guy? And what made insertion sort? Now insertion sort's usually the choice that people will choose when they choose a simple sort. Okay, they'll sometimes use an advanced sort, like merge sort or quick sort, and then for the last few items, they'll use an insertion sort. Okay, for the last 9 or 10 items. He's considered the more efficient of the 3 simple sorts. Okay, and what made him more efficient than the other 2 sorts? What's different about him? Hopefully you stared at this code long enough, you started to notice what was different about this guy. Yeah. So he had the same outer for loop, so the same n times for his outer for loop, still looping n times, but his inner loop is a while loop. So he doesn't necessarily have to happen n minus 1 divided by 2 times. He can happen less than that sometimes. Sometimes he'll happen that many times, n minus 1 divided by 2, and sometimes he'll happen less. Okay, because it's a while loop and not a for loop. A for loop is set in stone how many times you're going to loop. A while loop is not set in stone. It could differ. So sometimes this algorithm is more efficient than the other 2. Okay? Now it still does the swap within the while loop, okay, which made it a little bit more inefficient still. But, right? But you were able to calculate those times. Okay? So remember that you are actually able to calculate these times. Okay? So think about it. When we're doing random sorts, whether it's random or not, we're still going to compare that many times because it's a for loop. Okay? We're still going to swap this many times. Okay? Now notice I could calculate my swaps. Now my swaps in random, you might say, well, you can't really calculate that. You really got to test it. But what did you notice about these? Well, for the easy ones, because you probably didn't do these 2. These are the 48-hour ones. Okay. What did you notice about these? The simple ones. In comparison to each other and to this. Yeah, they're about half. They're about 50% of the time you swap. Okay? Sometimes a little bit more than 50%, sometimes a little bit less because it is random. Okay? But about 50% of the time that you loop, in those loops, you'll swap. So those numbers were about 50% of these numbers. And if you didn't want to run it 48 hours, you could just say, hey, you're 0.49% of that guy. That would have been a good guess. In fact, that's what I did in my spreadsheet here. I just said, okay, yeah, you're 0.49 of this guy over here. I'm not going to sit here and wait for you to run for 2 days, okay? So hopefully you guys did that, okay? And then for your selection sort, how many swaps are you going to have? Because he was in the outer for loop. He swaps outer for loop number of times. How many times did the outer for loop happen? N times, okay? So he happens very close to n times. Okay, it's n minus 1. Okay. And then for your insertion sort, he does the swap in the while loop, so about half of the number of times, but sometimes the while loop doesn't happen. So he happened about 0.5 around times 2 of, how many comparisons there were. So you should have kind of, figured out these numbers. Just by looking at these two, you could have figured out the bigger numbers there. Okay? So hopefully you kind of derived that, looked at the code, studied it, got those numbers in there, okay? All right. So I'm going to leave the rest because I'm hoping that people will get this done before Sunday, before I grade it, okay? So if you maybe thought, oh, I can't calculate this because my computer's taking too long. Make sure you actually do look at the code. You can figure out the other two, the in order and out of order. You can actually figure out, just by looking at the code, how many times it compares and how many times it swaps. And if you can't, run it for the two smaller values. Even run it for like a 2,000 or 3,000, and you'll start to see a pattern. And then you'll be able to kind of see what those other bigger numbers should be. Okay? So I plan on grading this Sunday, so it'll still be late, but some points is better than 0, so make sure you guys get this in and kind of study it, okay? Because this is something that you should know. These simple sorts are something you're expected to know. They really are simple, okay? You should be able to kind of code them, actually, okay? Just by, hey, I can just code this on the board kind of thing. All right, so you should be able to, they're not that complex, okay? You just remember that they're all kind of similar, okay? Because if you look at interview questions online, if you guys ever do go to a programming interview, they might expect you to know these things and be able to write them out, okay? Or at least write out the algorithm. All right, so the simple sorts are something that you guys should know. All right, and if you do look at the code, it makes sense why these numbers are the way that they are. All right? And your textbook goes into why these numbers are this way, too. So remember to look at your textbook, too. All right? Cool. Okay. So that's enough on that guy. Let's get into recursion, then. So recursion's pretty cool. And I prepared this slide, and I haven't posted it yet, and I haven't posted it yet for a reason. Okay, I will post it soon. All right. So what is recursion? Hopefully you guys have read in your textbook, and you would have read this in your first paragraph here. So sometimes it's difficult to define an object explicitly. However, it may be easy to define this object in terms of itself. And this process is called recursion. For instance, the picture shown in Figure 1 is produced recursively. First, an original picture is given, then a process of successively superimposing centered smaller pictures on top of the previous picture is carried out. And in other books, they'll say, okay, the kind of comparison of having two mirrors face each other. You have a bathroom with two mirrors. Actually, I do at home have a bathroom with two mirrors. And you can see infinitely many mirrors. It goes on for infinity. Okay. That's kind of, a visual of what recursion is. In programming, recursion is a function that calls itself repeatedly until a base case is reached. Okay. And here's an example of our factorial function. And we'll get into him. We're going to write him in Maple. Okay. So how does factorial work? What is factorial? You guys know what factorial is? Everybody knows what factorial is. What's the base case for factorial? What's the one case that's not based on any of the other cases? You can see right here. When your n equals 0, that's our base case. And here's the recursive part. And I copied this from offline, and they named their function with a capital letter. Oh, that's so bad. But whatever. So you can see here's the recursive call right here. Okay, so it's a function that calls itself. And at first, if you've never seen this in programming, the first time you see it, you're like, oh, how does that work? But it works because of this base case. Okay, so eventually, n has to get small enough to reach the base case. Okay, and factorial is one of those famous recursive functions you always look at. So we're actually going to make that in Maple today. Okay? All right. So we can use recursion to define sequences, functions, sets, such as, here's an example actually from your textbook. The sequence of powers of 2 is given by a sub n equals 2 to the power of n for n equals 0 to infinity, right? But we can also define a sequence recursively by specifying how terms of the sequence are found from previous terms. Okay. For the first term in the sequence, a sub 0 is 1, so that's our base case, right? That's the one that's not based on anything else. And then the rule for finding a term from the previous one, and they give this in the text, a sub n plus 1 equals 2a sub n for all n, for n from 0 to infinity. All right? And that makes sense to us, right? We all know that one. That was actually an example in chapter 2, I think, also. So here's how you would write that inside of Maple, or inside of a programming language. And since we're using Maple in here, I wrote it in Maple. All right? So remember that our base case up here, the terms of the sequence, a sub 0 equals 1. Okay? So note something about our procedure. Our procedure takes in that value, n. Okay? So if n is 0, that's where we return 1. There's our base case. You always put your base case first. Okay, so when you're writing these, well, usually always put your base case first in these recursive methods. Okay, for simple recursive methods, we always put it first. Okay? And then we have our recursive call. And so looking back, a sub n plus 1 equals 2a sub n. And how did this translate to this? 2 times recursive power n minus 1. Does that make sense to you guys, or do I have to explain that right now? So this is n plus 1. What if we replace this with just n? Then this would be 2 times a sub n minus 1. Okay. And here's the, well, not the trick with recursion. You just have to remember these two things with recursion. First off, you got to remember your base case. Muy importante, otherwise you have an endless recursive loop and your computer will explode and start smoking. Okay, that's what happens. Okay, so you got to have that base step. And then number 2, when you do the recursive call, the parameter has to finally reach that base step. So if n equals 0 and n is some number, it needs to get smaller. So when you do your recursive call, when you're sending that parameter in, it's the only thing that this function can remember. Remember, when a function's called, it doesn't remember anything from the outside world. Okay, it doesn't remember anything except what you send in as your parameter. Okay? So if it needs to reach n equals 0, n needs to get smaller. It can't get bigger, it needs to get smaller. So 2 things with recursion. Base case, and your parameter needs to reach the base case. Okay? All right. And this does actually give you that recursive power of 2. Or not recursive power of 2. It gives you 2 to the power of whatever. So 2 to the power of 3. So we send 3 in as n. And sometimes when we're first learning recursion, it's good to write out our recursive calls and see how they're working. Okay, so the first time we call this thing, I'm just going to write my function as r. What do we give it? We give it the number 3. It goes into the function. Is 3 equal to 0? False, right? So it returns 2 times, so this guy's going to return 2 times, but then it calls the recursive call. Okay? And what does it call the recursive call to? 3 minus 1. Sends in 2. 2 is not equal to 0. Goes to the recursive call. It'll be 2 times the recursive call of n minus 1. Okay? All right. We send in 1. 1 is not 0. Again, we call that recursive call. And remember that these are all stacked inside of your memory. These are all pushed onto the stack. Okay, and remember that these functions can't see each other. They're just pushed onto the stack and they're waiting to finish. Okay? Until this guy's waiting for this guy to finish, this guy's waiting for this guy to finish, and this guy's waiting for this guy to finish. Okay? So now we call it with our argument of n equals 0. Our base case is reached, n equals 0. What do we return? We return 1. So this guy is replaced with a 1. Now he can finish. So 2 times 1, obviously 2. Plugs it in. 2 times 2, obviously 4. 2 times 4, and it returns the 8. So something else you got to remember about recursion is it moves down and then it moves back up for simple recursion. Sometimes you can have multiple pathways because you can recursive recall multiple times. Okay?
So the reason why this works is because when it gets to return, it runs it again. And the last result is going to return the last.
It finally stops and doesn't call itself. And then it returns to this function call that was hanging in memory. He's waiting. He's just sitting there waiting. He's on the stack. His variables are pushed on the stack. Okay? He's popped from the stack when this guy returns. And then he's, oh yeah, I can continue on. I can say 2 times 1 now. And then this guy was waiting. And he's like, oh, okay, I can finish now. I got what I needed. And then this guy's waiting. He says, oh, okay, I can finish now. I got what I needed. And then this guy's waiting, oh, I finished. So you move down in your recursive calls, and then as your recursive calls finish, you move back up. Okay? All right. So it's good to kind of write those down at first. For the simple ones, it's kind of easy to kind of visualize in your head after a while. But as they get more complex, if you do this kind of writing down method, it does help. In fact, in my 39 class, we do recursion on paper for a while. Okay? All right. So here's another problem. This problem was another problem from your book, actually. So we use 2 steps to define a function with a set of non-negative integers as its domain. They have a basis steps. Oh, so this is how they say to actually do it, and then this is the problem. So your book says, hey, we use 2 steps to define a function with a set of non-negative integers as its domain. You'll have your basis step, which specifies the value of the function at 0, and then your recursive step, give a rule for finding its value at an integer from its value at smaller integers. Okay, so kind of like what I just said, but that's your book's way of saying it, right? All right. So here's that example. Example 1. Suppose that f is defined recursively by f of 0 equals 3, and f of n plus 1 equals 2 times f of n plus 3. And they figure it out. You know, they plug in numbers here, and they figure it out. But how would you code something like this? So, of course, we want to code it, right? We want to take this problem and turn it into a recursive function. So what's our base case? There's our base case. When n equals 0, we return 3. What's our recursive step? This is our recursive step. Notice he's calling himself. Now he said f of n plus 1. Now we don't want to add 1 because then we're going to grow. That's not cool. We need to subtract 1, right? We need to make n minus 1. Okay? So we say 2 times that recursive call of n minus 1 plus 3. Okay, because we need to make n smaller on the recursive calls, otherwise we're never going to finish this thing and your computer will explode. It really does. Try it.
I'll try it.
Actually, Maple just stops working altogether, and then you have to Control-Alt-Delete and tell him to stop it because he's just very ill-behaved. Okay, so, but this is how you kind of would write this type of problem. This problem is pretty easy to write. It's kind of easy to see your base case and your recursive step. Okay, and so you put your base case and your recursive step, and he does actually give you the same answer that they got in the textbook. All right. Should we do this one out, or can you guys do this one on your own out? Should we practice? Maybe you guys could do this on your own. But if you needed to, you would write them down kind of like that example there. If you can't see him right away, it's good practice to kind of write them down, okay, with your recursive steps. Remember that he goes in with like 4, then he calls it again with 3, 2, and then 1, and then finally 0. Then he comes back and finishes himself. The first time around, he'll return 9. Then first time around, he turns 3. Okay, right here. That's where our recursive step is. He returns 3. Then he returns 9. Then he returns 21. Then he returns 45. And finally, at the end, he returns the 93. Okay, so you can see that recursive step right here. All right. Another thing that we can do, but we're going to do it with the Fibonacci series, is you can trace your variables as you're running this thing too to kind of see how he's working. Recursion is not as intuitive to people, especially, people that are really good at programming, sometimes recursion is not intuitive to them because we're not used to thinking recursively in real life. Okay? It's one of those things that we're not used to. And once you get used to it, it does become more familiar to you, and it does become easier to kind of visualize these things. Okay? All right, let's try this one. Let's try it. Let's see if we can do this one. Okay? So this is kind of practice. And I'm going to do a couple with you, and then we're going to have to do these on our own. Okay? So this one's pretty easy. It says, this is an example from your textbook. It says, give a recursive definition of a to the power of n, where a is a non-zero real number and n is a non-negative integer. All right. So what's our base case? Actually, we can just start coding this thing. What's our base case in this guy? You guys should realize what the base case is. Yeah, when n equals 0, what is that integer going to equal? Whatever it is. 1. Remember, anything to the power of 0 is 1. So that's our base case. Base case, n equals 0. So that should be pretty easy to write. Okay. Now, I did already write these things, but let's write them together, right? Kind of practice in Maple here. And you guys could open Maple too if you want to. That would be cool. You guys are all pretty good typers. I think you could keep up. Or if you have MATLAB, you can use MATLAB. Okay. Or if you, well, I was going to say, if you want to use Java, I really don't mind either. But okay. I personally prefer Java, but okay. All right. So we won't even look at that. All right. So we need to set up our procedure first. And we'll send in n as an integer. So here's where we put our base case. And I encourage you to kind of write your notes in there as you go along. Remember, hashtag text is your notes. So first off, you put your base case. And what was our base case again? N equals 0. All right. So if n equals 0, then we know that we're going to have it to return 1. We've established that. And actually, I forgot my... I'm starting to write it in Java again. I got to differentiate here. Gotta remember, I'm a maple, no parentheses. Maple's so mean. Okay. Yeah, put that word then in there in the end if. All right. So we got rid of our base case. That looks cool. And then you think about your recursive step. All right, what will be our recursive step? For these simple problems, we don't have to make an intermediary variable. We could just say return, right? And then figure out our recursive step. So here's our problem over here. So what would be our recursive step when we're writing these things? Remember, we kind of saw it up there, actually. I showed you once before. That's another way to write a sub n. Or not a sub n, sorry. A to the power of n, a to the power of n, a to the power of n, a to the power of n. How do you write a to the power of n? Two. That's a weird looking. 2. And it has to be something that's making n smaller, right? Wait, not a. What is it, a? Oh, yeah, it is a. Yes. Very good. Stephen got it, yes. Okay. So it's the one we kind of just looked at, actually. So it would be 2 times the a to the n minus 1, right? Oh, yeah, it is like that, right? Yes. Okay, I'm mixing that one up, but whatever. How would we write our return statement? Actually, I can remember if we look at our PowerPoint here. We were just looking at this guy. We should know how to write this. And that's how we write him. Okay. And if we were looking at our slides, this is the one I was trying to remember. Oh, yeah, 2 times. And I did write him 2 to the n. And then he equals a to the n sub n plus 1 equals 2 to the a to the n. All right. So hopefully you can hash that out. Let's hash it out real quick, right? So how would you hash him out? So you could return. You want to call your procedure again, right? So 2 times your recursive power procedure, so your procedure name, whatever you called him. And then, of course, you want that n to get smaller. And we're just doing recursive powers of 2. And then, of course, we have to end our procedure. We ended our if, so he looks pretty okay. And then you could test him. I need to change the defaults on these computer to be a larger text. And so then you would, so it's 2 times, and if we wrote this out, if we wrote out all of ours, it would be 2 times, and another way that you can kind of write this, 2 times the recursive call, which will be 2 times the recursive call, 2 times. If we called it with 3, so if n equaled 3 the first time, this is for n equals 3. And this recursive call would be n equals 2. And then this recursive call would be n equals 1. And what does he return when n equals 1? Or not when n equals 1, n equals 0. Yeah, he returns a 1. So you can see it kind of moving back up. Okay? So that's another way that you can kind of write him out. Because it'll be 2 times recursive call, 2 times recursive call, 2 times recursive call, but this is n equals 0. And then you can move back up. Okay? All right. That one should have been easy. Hopefully it was easy. That one was easy. Let's try another one. We'll build on this. Okay, let's try factorial. Let's try making the factorial one in Maple or whatever programming language you have. Okay? Now for factorial, what do we got? If I say 5 factorial, what is that? Todd, what is that? Okay? All right. So what's our base case? Okay, 0. 0 factorial is 1. What is 1 factorial? 1. Okay, so we could stop at 1 actually too. Okay, some algorithms will stop at 0 and some will stop at 1. So our base case could be 1 or 0 because 1 times something is just itself. Okay, so our base case will be when n equals 0 or 1. Okay, so we could just say 1. Okay, and then n is getting smaller by 1 each time. Okay, so this factorial should be pretty easy to create. Okay, let's try it out. So what's our recursive step? Okay, so if you write it out like this, you can kind of see the recursive step. It would be n times 4 factorial. 4 factorial is 4 times 3 factorial. 3 factorial is 3 times 2 factorial. And 2 factorial is 2 times 1 factorial. And 1 factorial is 1, so you can move back up. Okay, so this factorial should be pretty easy to make. Okay, we can see the n, we can see the recursive call when we write it out like that. Okay, so let's do our factorial. You guys can practice. So if I wanted to do factorial, we would call our procedure. Hopefully this is all coming back to you. We're going to give them a value n. Our base case can either be 0 or 1. Whatever. To tell you the truth, factorial works with base case 0 or 1. And you can try both ways. And then we're going to change our recursive call to what we figured out on the board. It'll be n times factorial of n minus 1. Because that's what factorial is. And voila, we have factorial. Now, factorial is one of those classic recursive algorithms. You guys should know how to write this, no problem. Interview question, right? They will ask you to write this on the whiteboard. You should be able to write this lickety-split. So make sure you kind of understand what factorial is and how to write it recursively. Okay? Oh, it doesn't like me to use the factorial word, so we'll call him factorially. Maple's weird about those keywords and things, so. Huh?
Yeah,
Factorial is like a procedure name already.
yeah, it's an actual one.
And whenever that happens, I just put a little y at the end. I don't know. Factorially. Or my factorial. All right. So you guys should know how to do factorial in your head. It's not that hard, right? So, but you could test him. Maybe up to 7 is pretty easy to memorize. All right, so we get 50, 40, and that does look like 7 factorial. All right. Cool, factorial. Not bad. Factorially, I should say. Not bad. Okay, most people got that, hopefully. You've got our factorially. That made sense to them. Kind of stare at it till you get it, you know. Remember, you can write it out with the parentheses, or you can write them out in steps. Okay. So if this is hard. Another way that you can kind of do this, maybe I'll demonstrate with this guy here, is you can actually trace your variables when you're running this code to help you visualize what's going on. And when you trace your variables, that just means print them out. Okay. So you can do a little print. So if you wanted to, before you return, of course, you would put your print statements. And just tell yourself where you are. And you can print out n right there. And actually, if you wanted to concatenate these things, there is a function called cat. And then before your return statement down here, into these recursive functions, you can print out in recursive step, and then what your n equals right at that moment in time. So you can see him go out, and then see him move back in, and then give you the answer. And it's kind of like how we wrote it on the board. You'll see it print out like that. So this is called, tracing your variable n. Okay. So then when you run him, you could see he's in recursive step 7, 6, 5, 4, 3, 2, 1. Okay. And if we want to see him move up, actually we need to put a print after our recursive call. So we'd have to modify this guy a little bit. So we could say local m is assigned the value of this recursive call. Do you see why I'm doing this? So I can print him out before he returns. So if you want to print him out before he returns, you have to save him in a variable or print him. Okay. We should say recursive down step and recursive up step. All right. So note that what I did is I just took that function or that procedure call out of my return statement so that I could print him out. That's the only reason I moved him up there. Is so that I could print him out so that I could see when he moves down and then when he moves back up. And this will help you visualize your code too. So you can take any recursive function and do this so that you can start to visualize it. Okay? So if we ran this code, you can see him move down. N equals 7, 6, 5, 4, 3, 2, hits the base case. And then he moves up, 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 and then returns. Okay, and so you can do that to any of our recursive functions that we use today. I'm not going to do this to all of them, but it will help you kind of visualize what's going on in that recursion. It does help. In Java, I like to use the debugger, and you could step through and you can see the method calls pushed onto the stack and then see them pop from the stack, and you can watch your variables change. We do that in 39. Maple doesn't really have that. So we do old school debugging. We trace our variables. So everybody kind of got that guy, how to trace them, and factorial should be pretty easy. All right. Cool. Let's go on to our next problem. I got some more in here. All right, let's try the Fibonacci sequence. All right. Fibonacci sequence. We know our Fibonacci sequence. What's our Fibonacci sequence? Starts with 1. Then what's the next number? 2. What's the next number? 3. What's our next number? 5, 8, 13, 21, 34. Okay. So our algorithm is, this number is these two numbers. Okay. This number is these two numbers. So what is our algorithm?
N minus 2 equals 1, N minus 1 equals 1.
Actually, I make them write this algorithm out, actually in 06. In our first level programming course, we figure out how to write this algorithm. Okay. The algorithm's not that hard. You could look it up online if you wanted to. There's lots of, Fibonacci sequence is a pretty famous algorithm. Okay. But pretty much, okay, y equals 1. And then you do a for loop, right? And then you say z, or some other variable, equals x plus y. Okay. And then you say x equals y, y equals z, and then you loop that around, and voila, there's your algorithm. Okay? Well, you're always printing out z. So z would be our printout of our Fibonacci series. Okay? So you'd print out x and y right here, and then you start printing out z right here. Okay? Print z, or z is our Fibonacci sequence. All right? So what's our base case? In a Fibonacci sequence, yeah, it's our 1, right? Our 1 will be our base case. Okay? And then what's our recursive step? So let's write our base case first. I'm going to kind of cheat and write it this way. So let's see, we got text going on. We'll make him size 20. All right. So here's our Fibonacci sequence. Now this one, oh, I did print the variables. Well, I guess I could leave them printed in here. All right. So note that we have 2 1s in the Fibonacci sequence. Okay. So that is why we have actually 2 places where we could actually perform our base case. Okay, so n is going to start at some large number. He's going to get successively smaller. Okay. Until he either reaches a 1 or a 2. Okay. And then we want to return our 1. Okay, so maybe that'll help us write our other recursive call. So we know we're going to have our recursive call right here. Okay, otherwise we return, and what do we return? What's our recursive call? I think I heard it. Alan, what did you say? Yes. Or n plus n, yeah, minus 1. I know. N minus 1 and then n minus 2, actually. Right? Yes. So n minus 1 plus our recursive call again of n minus 2. Okay. So we do kind of, we changed our pluses to minuses kind of in a weird kind of way. You can kind of think of it as that way. And this is actually a pretty common recursive procedure, usually on every recursion talk and every book. They recursively call the Fibonacci sequence. Okay, so it is kind of a thing in lots of books, so you should actually know this guy. But looking at our recursive sequence, okay, what we're returning here, this guy here, is this guy plus this guy. So it's the n minus 1 plus n minus 2 is returning this guy. This guy is n minus 1. If he's n minus 1, n minus 2, plus n minus 2. If he's the n, then it's this guy is n minus 1 plus n minus 2. If he's n, then this guy is n minus 1, n minus 2. And remember, when we get to the end, this guy is n minus 1, n minus 2, and that's when we have to return the 1. Okay, so when n is 1 or 2, that's when we return that 1 value. And we're starting all the way up here, and we're saying this n is this guy minus this guy.
Well, it's never going to hit 1 if it returns that 2, right?
Or n equals 2. It will, because one of these will be 1, and then the second one will be 2. When n is 3, this will be 1, and then this will be 2. If you put n in as 3, just plug in n equals 3. This will be false. It'll come down here. This will be 3 minus 2, so this will be 1. And this will be 3 minus 1, so this will be 2. Did I say it backwards before? I think I did. But this will be our recursive call to 1, and then this will be our recursive call to 2. Okay. So this is our n equals 3. This is our n equals 4, 5, 6, 7, 8, 9. So remember, n is kind of our iterations. Okay? So when n equals 9, just plug in some numbers. And actually, we can plug in some numbers and maybe write this guy out. We'll do something small. We'll say n equals 5. So when we're calling this guy with n equals 5, the if statement's false, obviously. So then we call our Fibonacci sequence with n 5 minus 1, so it'll be n equals 4 plus 5 minus 2, n equals 3. Okay. Now this is a recursive call and this is a recursive call. So this one has to finish before this one does, actually, to tell you the truth. Okay, so this one's going to finish, so he's going to call himself. Okay. So if we plug in 4. 4 is not 1 or 2, so he's going to call 4 minus 1 plus 4 minus 2. He's going to call, okay. Now he's going to call it for 3 is not 1 or 2, so he's going to call it for 3 minus 1 and 3 minus 2. And what do those two guys return? 1. So this guy will return a 1. Should I do it a different color when they return things? So this guy returns a 1 plus 1, so he returns a 2 here. And then this guy's called. What is f of, or what's our Fibonacci sequence with 2? It gets into the if statement, it gets into the base case. What does he return right here? A 1. So then this guy will get the number 3. Okay. What happens over here? So this guy has to call. And he's going to call the Fibonacci sequence with the return of 3 minus 1 plus 3 minus 2. And what does he return? These are our base cases. He returns a 2. And then what does that guy return? All right. And we can run it and see how he works. And this one, actually, I did put some trace statements in there. I can recopy my other trace statements. Not that one. Actually, I did put the other trace statements in there, but that's okay. N minus 1 or n minus 2. I don't know if, oh, and oh, okay, that's what I did wrong. I knew I forgot something. Cool. So there he goes. You can kind of see how I wrote it on the board relates to kind of how he prints out there. All right. Maybe Fibonacci, it's a little, different. Okay. Let's move on to this one. All right, let's try this one out. And I did that one because he's in the book and he's good. All right, let's try this one. This one is fun. All right. Okay, so we have a number of bunnies, and each bunny has 2 big floppy ears. And we want to compute the total number of ears across all the bunnies, recursively. Okay, yeah, we could use a loop, but we're not going to do it with loops. Okay, or multiplication. We're going to do it recursively, just to practice our recursion, for the sake of practicing recursion. All right? So if we call our function and we give it the value 0, he should return 0 because there's no bunnies, they got no ears. If we give him 1, he should return 2 because 1 bunny has 2 ears. If we give him 2, he should return a 4 because 2 bunnies have 4 ears. Okay? And so here's kind of, this is in Java, but, or C++, well actually this is Java. This is how our function header would look in Java, but we can take this and we can make him into Maple. Okay, so let's write this recursive procedure in Maple. Let's see if we can hash this out. It should take us 1 minute, right? We'll see how long it takes us, but it should not take us very long to figure out this guy. So what's our base case? What's our base case? 0. 0 bunnies have 0 ears. Okay, so it could either be 0 bunnies, 0 ears, or 1 bunny, 2 ears. So this base case could be either or, because if we add in 0, who cares about 0, right? Okay, but if we add in 1, then hey. Okay. But we should make it work for 0, so actually we will make our base case 0. So that way if someone does send us 0 bunnies, we can tell them 0 ears. Okay? All right. So how do you write something like this? So you think of your base case, you'll write it first. Mirror. All right. So we're going to write this thing in Maple. Let me move him up the screen here a little bit. So we can call this one bunny ears. And he is a procedure, and we're going to take in the number of bunnies. And we can take him in as an integer. And here's our base case. So if the number of bunnies is 0, then return 0 because there is no ears to return. Otherwise, return, what do we return here? So what's our non-base case? So if it's not 0, it means we have at least 1 bunny. So how many ears does 1 bunny have? 2. So we're going to add in that bunny's ears. And then call it again for how many bunnies, because we've already added 1 bunny in. How many bunnies are left? There's n bunnies. Then there's how many left? Yeah, n minus 1 left. So we're taking out that first bunny's ear count. We're adding it in, 2 plus. And then we need to do this procedure again for the rest of the bunnies. Okay? So then we'll say bunny ears. We call them again for n minus 1. And then we're following our rules. Okay, that n is getting smaller. And it makes sense. Hopefully it makes sense visually. You can visualize that bunny, you're counting his ears. And then you have the rest of the bunnies over there. You need to count their ears. And you can do this with horses or dogs. They all got 2 ears. So you don't have to just stick with bunnies. All right. All right. So test him. Make sure he works. Oh, and I got all those new lines in here. Let me get rid of those. So you would just call your procedure. Hopefully you can figure out how many ears so many bunnies should have. So 3 bunnies should have 6 ears. So if I call my bunny ears with the number 3, he does indeed give me 6. That is a good sign. I can now figure out how many 3,028 bunny ears there are. We should be able to calculate that in our head. Okay. Or you can do other random numbers of bunnies. Okay, it should just be 2 times the number, really. All right. But that's how we do our bunny ears problem. Okay, that one was pretty easy. Hopefully that was easy, right? That one was easy. It kind of demos the point. let's try another one. Oh, actually, I've done enough demoing, and now we're going to play the recursive challenge. Dun, dun, dun. Let's play. The first student to program the recursive problem gets a prize. Yay. And I have a giant box of prizes. Can have anything from the prize box. And then big prizes are any book you want. And there's more books over here. Let me move my thingy. There are some microcontroller books. Lots of books. Well, these books were given to me by Mr. C. He retired, and he gave me a tremendous amount of books. So if you like electronics books, these are electronics books. And then these are programming books. Some of them are a little bit aged, but they're still okay, and some of them are still pretty relevant. Okay? Some of them are pretty okay. You might be able to sell some of these, right, on Amazon? I'm just kidding. Actually, hopefully you'll read them if you choose one. Okay? All right. Let's see. Do I have more up here? You can actually have any of these, too. Oh, yeah, I got some cool Adobe Flash ones. These cool ones. Some of them are actually in color. Okay, yes, Flash Professional is going away, but it's still cool. And Animate looks Flash. But note that Animate is crashing at the moment, so hopefully they'll fix it soon. Animate's taking the place of Flash Professional. You know me, you know I love Flash Professional. I love programming in ActionScript. All right. So these are our big prizes. Okay, you guys ready? Okay, they start out easy. They're actually not that hard, so we should be able to finish these. I don't know. I thought about having more than one winner. Let's see. Should we have more than one winner? Let's have 2 winners. And then I was debating whether we do this in teams or not. You guys want to try to do this in teams, or you want to do it individually? How many want teams? You want teams? Everybody? Who wants teams? Raise your hand if you want teams. You have to actually raise your hand, otherwise I'm not going to count you. Say teams. Okay. Non-teams? Actually, I have to count then. Wait, teams, raise your hand. 1, 2, 3, 4, 5, 6. And then non-teams? Actually, I think non-teams have 1. Okay, I guess we're going to do non-teams. Okay, you have to be on your own then. And you can program it in whatever. I don't mind if you program it in MATLAB or Maple or... Actually, I really don't mind Java. Well, I guess we should try to stick. Okay, we'll stick to Maple. We'll stick to our math languages at least. Okay. MATLAB or Maple. Dun, dun, dun. All right. Try this one. This one's really easy. Mark, set, go. And then if you get it, raise your hand real high, so then I'm like, okay, cool. You get it? I should have a little bell. You have to run up and ring the bell. Do I have a bell in here? Then it'll be part race to the front to get the bell. Oh, I have a bag full of RAM in here. I forgot about that. And I will be getting more prizes tomorrow at the GDC. It'll be quite awesome. Look, a nice FedEx bag we got going on. Todd? Yay. Todd and Stephen kind of raised their hand at the same time. So, wait, what was 3? Put in 3? 3 is, wait, what was 2?
It's just 3.
Yeah, 2 is 3.
2 is 3. 1 is 1. 0 is 0.
Oh yeah, 3 is 6. Okay, good. Todd got it. And then Stephen, you raised your hand at the same time. Did you get it?
I don't know. I think I got the top language part, but then it doesn't match that. Because you said the top has 1, and the next row is 2, but then you have 0 equals 0, 1 equals 1, and 2 equals 3. So I'm no longer sure.
And the next row down has 2 blocks, and so if there is 2 rows, because the n is the number of rows, then it will be 3 blocks.
Okay. Yeah, I didn't do that. I read it wrong.
All right, Todd, I think you got it. Yay.
Yay.
Okay, you can pick a prize. You can wait to the end to pick a prize, or you can pick it now. Hey, look at this. It's a VHS notebook. Oh, yeah, there's some cool stuff in here. Okay. Should we wait to the end? Or hurry up and pick it, or we have to wait to the end? Or you can pick actually a book, too, if you would rather have a textbook.
I think I'll wait until.
Or Skills for Success with Microsoft Office 2007. I think I can throw this one away. Yes, so let's get rid of this guy. Or does anyone want some CDs to hang up in the trees for decoration?
I think I'll wait.
Once I saw it, one of my friends decorated their Christmas tree with a bunch of CDs all over their trees. It's quite nerdy. Okay. Cool. Want to try another one? Let's try another one. I got another one in here. That one was easy. Hopefully that was easy for you. So if you got it, awesome. Hey, this one's a bunny one. It's building on our bunnies. But these bunnies are mutant bunnies. Okay? We have bunnies standing in a line numbered 1, 2, and the odd bunnies have the normal ears, and the even bunnies have 3 ears. Oh my God. Okay? Because they each have a raised foot. Well, let's say they're mutants. Recursively return the number of ears in the bunny. Okay, so it's building on our bunny ears problem, but now the even guys have the normal ears. Well, no. The odd guys have the normal ears, and the even guys have 3 ears. So see if you can do that. Remember, if you get it, let me know. Raise your hand high. And to do problems like this is great practice. So you should go home. I'll actually post a website where I actually got some of these from this website, where you can sit and you can practice these. And practicing them does make it easier and easier and easier. Okay? The more you practice, even these easy problems, the more you practice them, the easier recursion gets. It helps you think in that recursive manner. And they're all kind of the same because you know they all have to kind of reach a base case. Think about your simplest form of that case. Okay? Remember that you can have more than one recursive call. Hint, hint on this guy. Funny, I thought you guys would get this one super fast. Okay, I'll stop talking. Oh, in Maple? Actually, let me ABM. I'll show you the modulus operator in Maple. Very good. I forgot that we might not know that. Let me look it up. I think it is mod. Yeah, it is mod. It is the word mod is our modulus operator. It's a mod procedure. So it's mod parenthesis parenthesis. Okay? So you put mod 3, 2, and that would give you 1. Okay? Alan got it? Let's check it out. Good. Oh, I see pink writing. Oh, it's the one above it. Mod 2 does not equal 0. Return 3 times. Otherwise, return 2 times. Good. Yes. Perfect. Good. And did you test it? It looks like it's right. Okay, good. Good. Yes. Good job, Alan.
We did this on Java, so I'm like, what is the modulus operator?
Yeah, exactly. When you want to see if something is even, then it's when you mod 2, it should come out as 0. And you want to see if something is odd, when you mod 2, it should come out as 1. Okay, so good. Remember, a lot of these recursive problems are solved the same way. Okay. Okay, excellent. So hopefully you still want to work on it, but I'll let you work on it after. Are you ready for the next guy? I got 5 of these. We're on number 2. Okay. I thought these were kind of fun. All right. Now this one does use arrays, but you guys can use lists or sequence. Well, actually just use a sequence, right? So given a sequence of integers, compute recursively if the sequence contains a 6. This one is a little bit harder. Maybe I should, well, oh well. We already started it. We'll use the convention of considering only the part of the sequence that begins at the given index. In this way, a recursive call can pass index plus 1 to move down the sequence. The initial call will pass in index as 0. Okay, so what are we doing in here? We're just saying, hey, if this list returns a 6, or has a 6 in it. Okay, so if you gave it a sequence, I guess you could use lists here too. If you gave it a list, okay, with 3 numbers in it, and one of them was 6, it will return true. So notice that each time you're passing in the same list, and the list is not changing. Okay, what's changing? The index. And if we start at index equals 0, what's our base case? Think about what your base case is.
1, 2, 0.
Length, right? Number of items, NOPs. Okay. When our index equals the last item in the list. Now, actually, they started out at 0. Actually, in Maple, we'll have this be 1, actually, to tell you the truth. Our index will start at 1. Muy importante, actually. Our index will start at 1, not 0. This problem was written for people practicing in Java or C++. Okay, where indices start where they should at 0. In Maple, they start at 1. All right? So remember that your first case, when you call it for the first time, this will be a 1. So you're counting, right? You're 1. And your base case will be when that guy equals number of items. Yay! Peter got it. Okay, good. And you wrote it in MATLAB?
My MATLAB,
Huh?
my MATLAB ran out. I need to buy it again.
Oh, okay. So you just wrote in Notepad.
Yeah, well.
Right on.
Yeah. Sorry.
Let me look at him.
Yeah.
So,
Just as bad.
I equals the length, and we return
For the end.
false. And if this I equals 6, we return true, and then we return yes, I believe that will work.
Okay.
What do you
Yeah.
think? Let me plug in a number.
Yeah.
1, 2, 3, or 1, 6, 3. Okay, cool. Right on. Oh, you tested him? Let me see your tests.
Hmm?
Were you testing him?
Oh, yeah.
You're just running him through. You have to let me look. I can't look that fast.
What? Oh, sorry.
Okay.
Okay.
Okay. Okay, cool. Yay. Cool. Yes. Good.
Suck at
Okay, cool. Good. Now that one was a little bit harder, but that was cool. Okay, so hopefully we kind of got that one started. We're going to move on, but remember you could practice these at home, so I encourage you to. I'm going to post the answers, but don't look at my answers. Try to do them on your own. And then if you can't get them, then you can look at my answers that I posted, okay? So, and I'll also post the website where I got this so you can practice too, okay? All right. Oh, shoot. Now this one was a string problem, and actually, have we done strings in Maple? We have not. So let me get another problem actually. We don't want to do that one. Why did I think to do that one? I don't remember. We will do... We haven't done string manipulation in Maple, so here is a good one. I love this one. Okay, this one's easy. And we figured out how to do our mod operator, so. All right. We'll try out this guy. So given a non-negative int n, compute recursively, no loops. Remember that we can do this with loops. And to tell you the truth, loops work more efficiently than recursion, always, okay? Why do we even have recursion? We'll go into that. But the count of the occurrences of 8 as a digit, except that an 8 with another 8 immediately to its left counts double. So 8818 yields 4. Note that mod by 10 yields the rightmost digit, and you guys should know that. Okay, whenever you mod something by 10, it gives you the ones place. Okay, well, divide by 10 removes the ones place. And you guys should know that, okay? All right. And actually, this one is a different version of... So we'll put both of these up. So you could solve either one. That one is a little bit hard. So if you solve either one, you can go for the easier one or you can go for the harder one. Okay, we'll put both of these up. So this one will be a double. And if you get both of them, then you get double prizes, right? All right. So this one kind of is like the same thing, okay, but a little bit different. Return the count of the occurrences of 7 as a digit. It doesn't have the 8 next to each other. Okay, so for example, 717 yields 2. Note that the modulus, of course, you guys know that stuff. So this will be the easier version. This one's a little bit harder, but they're kind of the same. So see if you can do either one or both or the other, okay? So you can pick one. Should we say this harder one is double prize? We'll say the harder one is double prizes. Double prizes for the harder one. Now you want to put all your eggs in one basket, you know, start coding this one right away. All right. See, that last one's double prize. And then this one will just be our single. All right. Just think about your base case. Remember, you're going to make something smaller and smaller. What are you sending in? You're sending the number. He's the thing that's going to have to get either smaller or smaller, right? The divide by 10 thing kind of tells you that. Right? And then what's your base case? When he is 1 digit, right? All right. Note what you're going to return. What does it tell you return? If it's a 7, then you'll return 1 plus, dun, dun, dun. So when you are going to have some if statements, and in those if statements, you'll have the other recursive calls. And this one is considered a little bit more difficult than the other ones, okay? So we did end on this note, so end with the more difficult one here. But see if you can hash it out. Once you start typing it, you can start to see too, or once you start thinking it through, okay, you got your base case down, you know that it's going to get smaller. Okay, you know in certain cases you're going to add something, and in other cases you're not. So you're going to have different types of recursive calls. One's going to add something to the recursive call, one is not. Okay. Actually, hindsight bias, maybe we should have went over the answers to the other ones, but that's okay. We'll go over them in a second. Oh, I thought you had it, Todd. You were like, what? And being able to do these really does help your coding ability. Okay.
Yeah, but incursion is like conception. Dive into. Human brain wasn't built to dive. It was built to think horizontally, not really.
Yeah, we're just not used to it, so. Once you start to get used to it, it starts to make complete sense, actually. There's a lot of problems in a computer that almost have to be solved recursively because to write the code for them would be tremendously hard. Remember, anything that can be solved recursively can be solved with loops. Okay? And recursion is always more inefficient. Okay? Because it does use a lot of stack. You're pushing all those processes on the stack. Okay, and I'm putting up this one on the left here because this was the last one we did, and it's kind of like this one a little bit. So if we're thinking about that last one, I should have went over the answer to the last one, but I'll just put it right here so you can kind of look at, okay, this is how you would have solved that last one, and it's sort of how you're going to solve this guy. Okay, a little bit. Did you get it, Victor? Yeah, so, yeah, are you guys going to turn in your work? I'm just going to give you class points for doing it, right? So I'm pretty easy that way for today. But they should, you should have them down. You should at least attempt them. And you should have, the ones that we did together kind of finished. Actually, let me... So here was that last one. And remember, the last one looked like this. I'll put them up here. Now I'm just putting the last problem up just so you could see, okay, because I actually probably should have went over him, but that's how you would do him right there. Okay. All right. Just so you could kind of, register how we did the last one and then how you're going to do this guy. He's not all the way the same or anything like that, but he's just, you're going to have your branching statements. You're going to definitely have to have some branches in here because there's different cases that you have to take into account. The first case is there's 1 8. The second case is there's 2 8s together. And the third case is just a normal digit. So remember, you're going to have those 3 cases. Besides your base case, right? For that third problem there. And I just posted that first problem just so you could look at the code and see here. Can I get rid of this sidebar? There we go. That's better. Think about your base case, what's getting smaller. Here, I'll come around and maybe give you guys a hint. This one is harder. Kristen, did you get it? Oh, I was like, yes. To match delimiters. Okay, so mod. Plus 10 divided by 10 equals 7. Count equals 1. And remember, it doesn't remember count from recursive call to recursive call. Count will always be new. So you should always return count. Yes, Steven, good. Count 7. So you did the first one, right? Yeah.
Yes.
So n mod 10, if n equals 0, then return 0. If m equals 7, then return 1 plus, blah, 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 else return 0 plus. Good, yes. Yay, Steven, woo! Oh, and some people are leaving, but remember to turn it into the class assignment. Okay. And I'll post the answers to these, and I encourage you guys to kind of practice them. We're going to go into recursion again for linear search, binary search, and all that stuff next week. I did post an assignment. I posted it early, so you guys can read the recursive assignment, okay?
Wait, we're turning the same?
Mm-hmm.
Wait, but I changed...
That's kind of how I take Roy's.
Oh, I've been changing the same...
Oh, I know. I grade these ones easy.
Oh, then do you just want this one?
In fact, let me